All right, thanks for coming. Today we're gonna continue where we stopped yesterday. I'm gonna deal with 5 operations of set operations, right? Union of sets, intersection of sets, complement of a set, difference of sets, Cartesian product of sets, right? Yeah, we're gonna deal with all those things in this video. But before I start, right, please, I beg you to subscribe to my channel, like and share this video, leave comments or questions under the video, and then I will respond to your questions and comments as soon as I can. Okay. But before I engage in today's activities, right, there is something I forgot to mention yesterday. I want to deal with it. I deal with it, and then from there we'll move on to this set operations. Okay, thanks. All right. Recall that yesterday I showed you an example of. I drew that picture yesterday. I showed it to you yesterday, and we talked about universal set. Now, mathematicians like to use. See all those 5 sets there, the set of natural numbers, the set of whole numbers, right? The set of integers, the set of rational numbers, the set of real numbers. What normally happens, mathematicians usually start with any of these sets as the universal set, right? From there, then they go to solve their problem, because you have to do that. If you don't do that, you're gonna make mistake. I will show you in a little bit about that. Now, recall also that I told you, we talked about the Cartesian coordinate system before. You draw a line. I mean, you can put it, vertical line, and then put 0 here. You put the points, right? Okay, I want to talk about this. See this? From 1, I could have chosen any point, but from 1 to 7, right? I cut it out and put it here. That's what you're looking. That's the segment you're looking at there. 1 to 7, right? Now, this 1 to 7 is a segment of the Cartesian coordinate system, right? It's a segment of it. It has a special name in mathematics. It has a special name. Actually, it has 4 names, depending on which side is open, which side is closed. Let me show you what I mean. You can redraw it like this: 7 here, 1 here, right? And then you can say right here is open. That means 1 and 7 are not included in this segment here. Yeah, 1 and 7 are not included, right? You can also say, draw another one right here, okay? And then you say you want to include 1 and 7. So what they do is you draw it like that. You draw it like that, means 1 is included. There's no hole. You learn about this when we use this when we go to calculus. There is no hole here. That means 1 and 7 are included in that segment, right? If 1 and 7 are not included, you draw a circle, making a hole. You see the hole there. You don't shade it out. Okay? Now, there's another situation you can have. I draw another one. You can have a situation like this: 7, and this is 1. Let's say 1 is included, but 7 is not included. What do? You shade 1 there, close the hole, and leave the hole in the 7 like that. There's a hole right there in the 7. Or it can be the other way around. See, you can have a situation, 7, 1. You can have a situation where, basically where 7 is included in the problem of whatever you're describing, but 1 is not included. So you draw it like that. That's a hole in 1. So all these are 4 ways. These are 4 ways you can describe this segment here. This segment here. Those are 4 different ways, that, things can happen. Okay, when you're solving a problem. This thing is called interval. It's called interval, right? There is a notation for it. I'm gonna write down out for it. This is called, this one here is called open interval. Open interval. Just pay attention. You'll see this is very important. Open interval is written like this because 1 and 7 are not included. You write it like this. That's open interval right there. And then this one here is called a closed interval. Closed because there's no hole anywhere. Closed interval, right? And it's written like this. See? That means 1 and 7 are included. There's no hole anywhere. Now, this one is called half open. This one is called half open. Of course, it's half open from this section of 1, right, from the left. So it's written like this. 1 is included, 7 is not included. So you write it like that. That shows that 1 is included, 7 is not included. The same thing with this one here. This is also a half open, half open interval, right? But it's open from the left and closed from the right. So you write it like this. 1 is not included because there's a hole there, and 7 is included, right? You write it like that. So you need to know these. As I was making this note, I realized one thing. You remember when we did also Cartesian coordinate system, right? Right, 0 here. I told you that any point, this is x, this is y can go down here. I told you that any point here can be identified with what is called ordered pair of number. Like you go down here, you find the value of x, let's say it's 2, and you go here, you find the value of y, let's say it's 2, and then let me see, let's say this is 3 here, and that's the y is 2. So you write it, you write x first. It's written like this, x first, and then y second. You write y like there. This is called ordered pair. It's called ordered pair. It's ordered because x is first before y. They call it ordered pair, or you can say it's a coordinate point, in the Cartesian system, right? Coordinate point. But check this out though. Sometimes there is a confusion between this Cartesian representation of ordered pair with the open interval. See the open interval right here? If you look at them, they look the same. But it's nothing to worry about. That's how mathematicians design stuff. The thing is, when you're solving a problem, the context. That's why sometimes they say context is very, very important when you're describing any situation, any problem. So the context of the problem will tell you whether you're dealing with an ordered pair or with an open interval. Okay? So don't worry about that. Don't let that confuse you. So now let me continue with that and there. Remember our interval there is, remember we started with this? I said this is 0, this is 1, and this is 7 here, right? That's what we started with. 1, 2, 3, 4, 5, 6, 7. Yeah, 7 here. Okay. And then we'll have all those different types, the 4 types of intervals described between that, depending on what is included and what is excluded, right? Okay. Now, the Those intervals can also be described as sets, right? They can be described as set as long as you define what the universal set is. Whether the universal set is real number, natural numbers, whole numbers, you have to do that. If you don't do that, then the set will be, you come up with the wrong information, right? So, let me list our intervals again. Let me list 4 intervals using 1 and 7, right? Using 1 and 7, you will have, this is, let's see, let's call it A. A is an open interval, right? Between 1 and 7. 1 and 7 are not included, right? Okay, sorry about that. Let's say B is a closed interval. 1 and 7 are included, right? Okay, let's say C is half open interval, right? Half open interval, 1 is not included, but 7 is included, right? We'll write it like that. And let's say D is another half open interval, but this time 1 is included, 7 is not included. You see, those are the 4 situations I described earlier. So we use that interval. I want to use that interval for demonstration. Let's say you want to use this interval, you want to define them as a set. Then you have to start by stipulating your universal set, right? Normally it's done like this. The mathematicians will say mathematicians will usually say let 1 and 7 be element of real numbers, right? They could choose any set, real numbers, natural numbers, So this is the universal set. This is the universal set, and then from there, right? We can define A like this. A is a set. As long as you stipulate this universal set here, right? Then A is a set. A is a set described like this. It's a set of X such that X is less than 7 and X is greater than 1, and then you close it like that. That's the same meaning as that. You see? You see that, right? That's a set right there. B is also a set of X such that X is between 1 and 7. Still the same thing, but how do you stipulate that X between 1 and 7 in a situation like this? You go like this, X, right? Because both of them are included, you go, is equal, X is less than or equal to 7, or greater or equal to 1. That's how you say that. Okay? That's basically how you describe that set. But anyway, C is described like this. It's a set of X such that, right, X is less than or equals to 7, right, and greater than 1. That's how you describe that. See, because 1 is not included, 7 is included. One more. D can be described like this: a set of X such that, right, such that X is less than 7 and greater than or equal to 1, because 1 is included, right? So that's how you describe those 4 sets. If this is a real number, if our universal set is a real number, notice something. If you real number, notice that hang on a minute, let me see something. Notice that A is the same thing as, you can write it, list it, whatever is included, A will list it like this. A is the same thing. Actually, let me make a space, that way you can see everything. A is the same thing as um, since 1 is not included, 7 is not included, A will contain 2, 3, 4, 5, and 6, because 7 and 1 are not included, right? And then B will contain what? Look at B carefully. 1 and 7 are included. B will be 1, 2, 3, 4, 5, 6, 7, right? Everything will be in there. All that thing will be in there because everything is included. And then the same thing, the half open intervals, like C will be written as it will contain. Now notice in C 7 is included, 1 is not included. So C will be 2, 3, 4, 5, 6, and 7, right? Because 7 is included. The same thing as we do D. D will be there. 1 is included, 7 is not included. It will be 1, 2, 3, 4, 5, 6. 7 is not included, right? Okay, so make sure you understand this. If you understand it, it will help you to see the next example I'm going to give you. Look at this example. Check out this example. Suppose I say, you know what? Let me do it over here. Let me get another page. Suppose I said that the universal set we're using is set of odd numbers. We'll call it odd integers, or we can say odd real numbers. But let's say odd integers, right? You know what is integers? Let me see. Integers are 0, 1. Keep going, right? And then there's a negative. There are negative 2, negative, there are negative 1, negative 2. Keep going that way, right? Okay. So let's say our universal set is set of odd integers. Remember, odd, that's even odd. And then I will give you this. Look at this. I say J is equals to J is equals to 2, I'm sorry, not 2, 1. J is equals to this thing here. And then I say K is equals to this thing here. 1 and 7, right? You see? And then I say T is this thing here. 1 and 7. 7 included there. And then I say V is equals to this thing here. 1 included but 7 excluded, right? Okay. Notice that the elements of this can be listed as these are sets. This is let me see, 1 and 7 are not included, and you're looking for odd numbers, right? So the odd numbers between 1 and 7 is there are 3 and 5, right? Because the rest are even numbers. The same thing here. Odd numbers, 1 and 7 included. Odd numbers there, 1, 3, 5, and 7, because 7 and 1 are included, and 7 and 1 are odd numbers. And then we'll do the same thing here. Odd numbers there, see, 7 included but 1 is not included. Odd numbers will be 3, 5, and 7. See? And then this one, you do the same thing. That one is included but 7 is not included. So odd numbers there. 1 is an odd number, right? Odd numbers will be 1, 3, and then 5. You see what is going on? So depending on the definition, the universal set you started with, the thing can be different, right? What you come up with can be different. Supposing I change that, let's change that to even numbers. I wanted to do this in one. That way you can look at it. But let's change the question right here. Let's change the universal set to even numbers, right? Let's say our universal set is a set of even integers, right? Even integers. See, you will come up with different things than you came up with here. Watch this. Then we're gonna still do the same sets here. I'm gonna write it that way. I want you to see everything in a side by side. Then, if that's the case, if let's supposing our universal set is we change it to a set of even numbers, right? Even integers, specifically integers, right? Now, I want to show you what what we did above will change. We still use the sets J, K, T, and V. Okay, so then you see that J will now be the same thing as, of course, we know it's 7, between 1 and 7, right? It will be, since we're looking for even integers, right? It will be 2, 4, 6, right? And then K will be, since 1 and 7 are included, but 1 and 7 are not, they're not even anywhere. So, but they're included. So it will be, we'll write it like that to show what we're working with. And then it will be this. It will be 2, 4, and 6. That's what we're gonna have there. All right. So let's do T. T will be what? T will be 7 is included, but it doesn't make any difference. It will be let's see. It will be 2, 4, because you're looking for even integers, right? It will be that. And then V will be, even integers will be 2, even though 1 and 7 are included, but both of them are not integer. I mean, are not even. It will be this. These are all even. We'll have. Notice they're all the same. They're all equal. See? In this case over here, they're all equal sets, man. They contain the same element. But over here, they're not equal. Before, I see, they're not equal. That's why it's good. I wanted to do this thing to show you why it's good to, to have your universal set properly defined. If you don't properly define it, you get the wrong information, man. You're not gonna be getting the right information. You see. If we change our universal set to real numbers, we'll get totally different 4 sets. All right, so let me leave it there. That way we can go to what we want to accomplish today. All right, the first concept we're going to describe today is the union of sets, right? Let's say we have 2 sets, A and B, right? Then I define what I mean by the union. The union of A and B is the set consisting of all the elements of the 2 sets. Right? That's a reason why I define it like this. If you go online, you see different kinds of definitions, but they're all confusing. So the union of A and B is written A union B. Just try to understand the definition. If you understand, just read the definition until you can understand it. Basically, you say it consists of a set. It's a set consisting of all the elements of the 2 sets, right? And it's written like that. Notice that this thing here is called, there's a word, if you ever use latex, If you use letters to do mathematics, they call this cup. Cup. I'll get to that in a minute. It will help you remember. See, it looks like a cup. They call it a cup actually in LaTeX. It's called LaTeX. It's a program used to do mathematics. Alright? So that symbol is a cup. Now, I can write that thing. I can write that thing in there. Let's write it in what they call in set. What is that? Set builder notation, right? If we write it in set builder notation, remember we talked about that. That's one of the ways you define, you list, describe or represent what is a set, right? If we write that in set builder notation, we're gonna say A union B is the same thing as X. We didn't write it this way before, but it's okay. It's okay. This is a different way mathematicians write stuff. X is an element of the universal set, right? Such that, yeah, it's okay. You can see written like this in books. Such that X is an element of A, right? Or X is an element of B. And then you close the bracket. That's how they write it in set builder notation. Don't let the word or confuse you. That's why I didn't put that word. Many definitions you see, different books, different places, they use the word or. They use the word or somewhere in the definition. I don't want to do that. You don't have to. We don't have to insert the word or in the definition. Just that definition I gave you there will help you. Okay, I will give you examples. Let's go to the other side because they go together. Let's go to intersection. What is an intersection? An intersection of set A and B is the set consisting of the common elements of the two sets. Common elements of the two sets. Do you understand? Pick up on the language. It says the common elements of the two sets. Pick up on that. Common elements of the two sets. Pick up on that, man. Pick up on the word common. Union says all the elements of the two sets. This one said the common elements of the two sets, okay? Now, here is how they write that one. This is how they write intersection. A intersection B is written like that. Now, I can also write it in the form of set builder notation. Insert builder notation, right? It can be written like this: A intersection B, right, is equals to X element of universal set such that X, right, is an element of A and X is an element of B. That's all. See, the difference between those two is the or and. And then notice, before I forget, this thing in LaTeX, LaTeX creates a program for solving mathematical problem. This thing is called cap. They call it cap over there. The word is telling. Cap is like cap you wear. And the other one is called what? It's called cup. Cup for drinking something. Notice the word cap has A in it. A and cup. Cup, when you pronounce cup, there's O there in cup. O is in cup. Cup. And is in cap. Okay, so if that helps you to remember this thing here and that and this thing here, that's okay. But as long as you remember my definition, right? Union is a set consisting of all the elements of the two sets. And then the intersection is a set consisting of the common elements of the two sets. That's what you need to pay attention to, the definition. The definition will help you solve a lot of problems, okay? If you can remember, just memorize it or try to understand it. You don't have to memorize. Try to understand what it's saying. Let me give you a couple of properties, right? Those two things got properties that are very, very interesting. Properties, I will write it like that. Let's say properties, right? Properties of A union B, and then we'll do properties. These are good properties, but it helps you to understand the properties. Help you to understand the definitions too. Okay, properties of A intersection B. Check this out. Okay, the first property here is that A union empty set, that's the symbol for empty set, is equals to A. The second property, A union the universal set, right, will give you the universal set. 3, A union itself, A union A will give you A. Now, let me try to explain that. A union empty set, right, will give you A. Why? Because remember the definition of union. Union is all the set consisting of all the elements of both sets. Empty set got nothing in it. It's empty. So the union will naturally give you A. Let's go to the second property. A union. What is universal set? Universal set is a set. A is inside the universal set. A is a subset of universal set. So naturally, if you unite them, it's gonna give you the union will give you the universal set, right? Just as much as empty set is inside, it's a subset of A. If you make a union of them, it will give you A. Here, if you make a union of this, because A is inside of U, it will give you U. Look at the number 3, right? We've done number 2. Number 3, A union itself. Well, A contains itself. So if you unite them, the common elements there will be the same. You remember, you're not supposed to repeat elements, right? So if you unite A with itself without repetition, if you don't repeat anything, you get A. Okay, so let's do the properties of intersection. The first property is A intersect with empty set will give you empty set. I will explain that. 2, A intersect the union. I'm sorry, not the union. The universal set, it will give you A. Number 3, A intersects itself. It will give you A. All right, let me explain that. The first one is kind of very simple because, again, you gotta go with the definition. The definition of A intersect B is the same thing as the common elements. The common elements belonging to those two sets, right? The common element belonging to A and the empty set is empty set. Empty set is empty, and then A has an empty set, so that's the common element there. Look at A intersect with the universal set. Again, what is the common thing there? When you intersect them, the universal set has more sets, but A has specific sets. So they will have whatever A has in it, that's what they will have in common. So that's why that one is A. And look at number 3. A intersect A. If you intersect A with A, what do you get? Think about that for a minute. What is the common element they have? They both have the same element, so they will have the same thing in common. So the same thing they will have in common is A. So that's how you try to explain that. Read it carefully, try to understand it, and then, you should be able to make something out of it. All right, before I give you an example, let me use this image to demonstrate the meaning of union and intersection. This image you see there is called Venn diagram. We will get to that later. We're gonna deal with that later, but I want to use it to that way you can see the image, the picture of what they mean by union and intersection. Remember, what is the image here? Let me use a red pen. The image here represents union, and the image here represents intersection, right? Again, let's start with union. What is the definition of union? The union of two sets is a set. It's a set consisting of what? It consists of all the elements of the two sets. So you see the shaded region there contain the union. The union is everything, all the elements of the two sets. If that will help you picture it, then good. And then let's go to the second picture. What is intersection? Intersection, according to how we define it, is intersection of two sets is a set consisting of the common elements of the two sets. The common, not all of it, the common, whatever they have in common. You see, whatever they have in common, there is they intersect right there. Somehow they intersect. Sometimes, where the shaded area is what they have in common right there. Sometimes they can intersect like this, they can intersect like that. It doesn't have to this is just for explanation purposes. Sometimes the things can be as big as that. Sometimes it can be like that, depending on the situation, you see. So keep that in mind. Keep that image in your mind. It will help you to understand. We're going to go do a couple of examples, okay? All right, let's work a bunch of examples. It will help you understand the concepts, okay? Look at the example I put there. You have those three sets, right? Now, what we're gonna do, we're gonna find a bunch of unions, right? Let's do A union B, right? According to that, what is A union B? What did we say? A union B is a set of all the elements of the two sets, right? So A union B is the elements, all the elements of those two sets, right? So we'll go. That's 2, 3, 6, 7, 8, 9. But we don't want to do any repetition, right? So it's 2, 3, 6, 7, 8, 9. We got all of it. You just put all the elements of those two sets into there. And then what of A union C? Again, we'll follow the same steps, right? We'll put all the elements there. 2, 3, 7, 8, 9. These are elements common to A and C, right? You see that 2, 3, 7, 8, 9. Yes, we got all of it. Now let's do B union C. What do we get? We get 3, 6, 7, 8, and 9, right? Again, these are the things they have in common, man. I mean, I know all of it, the thing they contain together, all of it, all of their content. But you don't want to do any repetition, right? Because you see, they have 3, they have 6, they have 7, they have 8, right? We don't want to repeat it, then they have 9. Okay? All right, so let's do another example. Okay, so we do that example. We want to find T union V, right? T union V. What is that? Well, all the elements in both sets, right? We'll go like that. 1, 7, 8, 10, 12, and 19. So, we'll put them in order, right? That way they don't, we don't get confused. That way when somebody is reading it, it's easy to read. Here is another example. Notice that set S is letters of the word silent, and J is letters of the word listen. So we operate on it. We say what is the union of those two sets. The union is all the elements, right, combined without repetition. So we say it's S, I, L, E, and T. We don't have to repeat T, even though T is in both sets, right? We don't have to repeat I. We don't have to repeat S. This is what we got there, okay? And then we do another one. Okay, we'll do another example. See that those two sets. Set K is basically the letters in teams, like in team of workers, right? And P is the letters in terms. Terms is a verb. And then what we would need is the union. The union is T. We can't repeat anything. You just write the letters without repetition. Notice that it comes out as teams. Isn't that amazing? Look at that. So we didn't repeat anything, so we'll keep going. All right, notice the next example we'll have 3 sets, okay? So we're gonna, do a bunch of stuff. Let's do A union B, right? A union B, okay, know what is a union by definition? The elements, all the elements in those two sets, combined together without repetition, right? So we'll say it's 0, 4, 7, 8, right? Look at it carefully, that's what it is. A union B, 0, 4, 7, 8. That's it. Okay, now I want to make keep a lot of space for this problem. What of B union C? What do we get there? We get 4, 8, 10, 11, right? Okay, that's B union C. Okay, now what of A union C, right? We'll find 0, 7, 10, 11. Okay, now check this out. I want to do more. Suppose we want to find A union B, right? And then in bracket union C. We can find that. So you can join stuff like that. We did A union B already, which is this 0, 4, 7, 8, right? And then we want to join it with C, union C, right? You can write it like that. That's, it's proper. It's legal in mathematics. Then what do you get there? Once you do that, what do you get? You get 0, 4, 7, 8, 10, 11, right? Because you combine all those elements, right? Now, check this out. Suppose I do A union B and then union C inside, right? That's union, not union, like that. Suppose I do that, what do I get? Again, You can do it the way I did the previous one. You can say we'll have A like this, all right, and then we'll have a union of what? We already have this one here. B, let me see, B union C, right here. It's right there, right? And then we'll put it down here. 4, 8, 10, 11. And then we'll combine those two. If we unionize those two, what do we get? We get 0, 4, 7, 8, 10, 11. Notice something. Notice that these two are the same set, right? So basically that tells us that A union B union C is the same thing as A union in bracket union C. See that? So this is called something. It's called the law of association. The law of association is set to your law of association, like that. Or you can say associative law. Okay, so that's what that is called. So we'll prove it right here using an example. See, So let's move on. Let's move on. Actually, I want to do one more. I want to do one more law by example. Let's do one more. Okay, look at that. Look at that. B union A. We didn't do that before, so I went ahead and did that. B union A, you get that because this is B here, and this is A here. If you unite them, the elements together, you get 0, 4, 7, 8, which is correct. Now check this out. What of this thing here? A union B. We did that already before, right? We did that. Let's see. We did it here. And it's the same thing as 0, 4, 7, 8, right? Notice that they are equal, man. Notice that these are equal. So we say A union B is equals to B union A. So this is a law. This law is called commutative. They commute. They can change places. It's called commutative law. Commutative law, right? Or you can call it the law of commutation, right? It's the same thing. Law of commutation. It's the same thing, okay? So we'll do another example. All right, look at that example there. You have A, B, C, right? So let's do a bunch of stuff. Let's do A intersection. Now we'll move into intersection. When you form the intersection, you get a set, and this set contains the elements that those two sets have in common. Not all the elements, but the elements they have in common, okay? Look at A and B. Intersection A and B will give you this set. What do they have in common, A and B? They only have, let's see, they only have 9 in common, right? Yeah. Okay. Let's do A intersection C. What is that? What do they have in common? A and C has 9 and 13 in common, right? 9 and 13. That's what they have in common there. Let me clean this out here. Okay. And then let's do B. We'll do B intersection C. Look at B and C. What do they have in common? They have 9, they have 16, right? So we'll say 9 and 16 is all the stuff they have in common right there. And then we're done with that. Let's do another example. Let's do this example here. We'll do, all right, here is our example right there. A, B, C, right? Now, we want to find a bunch of stuff. Let's see. I'm looking to make sure I copied the problem correctly. Okay. Let's find the A intersection B, right? If we find that, you will get, this is what they have in common, 61 and 70. Look at those two sets, A and B. They have only 61 and 70 in common. Everything else is different. Okay. And then let's do A intersection C, right? What is that? Look at those two sets. What they have in common is this 2, 31, and 70, right? Look at it. Look at them carefully. See? A right there. Okay, 24, 31, and 70. And then check this out. Let's do B intersection C. What is that? What do they have in common? It's only 70. See? They only have B and C. This is B, got 70 here, and C got 17 here. I don't see anything else common. So that's it. Okay. And then we're done with that one. That's all I have there for you. Okay, the next problem you see right there, this next example is interval. 2 intervals. Look at that. A, 2 is included, 4 is included. B, 2 is included there, but 5 is not included. Now, suppose it say find A intersection B. Now, how do you proceed? Well, you can draw the intervals that way where they are set. You can draw the set. By the way, this is the union. The universal set there is the natural number. Okay, sorry, I forgot to put that there. That's what we talked about before, right? Now, if you draw the numbers, you will see that for the first set A, 2 is here, 3 is here, and then 4 is here. For set B, right? Set B, you have, now the 2 is included, the 4 is included, right? Remember, you do it like that. For set B, 2 is here, 2 is included, and then you have 3, you have 4, you have 5, but 5 is not included. That's a hole there. So look at those, see? Look at those two sets. What do they have in common? They have, because 2 is included, they have 2 in common, right? They have 3 in common, they have 4 in common, but since 5 is not included, they don't have 5 in common. So you say A intersection B is the same thing as 2, 4 inclusive. So you can write that as this: 2, 3, 4, like that. See, if you look at the graph there, that's what we just said. We drew that stuff right there. Okay, there is the next example we're gonna deal with, right? Yeah, you can look at it carefully. Then let's find A intersection B. What do those two sets have in common? A and B, they have only 3 and 6, right? Look at them carefully. Only 3 and 6. Okay, and then we're gonna find a bunch of stuff there. That way we can use them to demonstrate something. Let's say we find A intersection C. What is that? Look at those two sets carefully. They only have 1 and 3 in common, right? Okay. So let's find the B intersection A. Okay. Now look at those two sets carefully. What do they have in common? They have 3 and 6. Welcome. So you're dealing with B and A. They have a 3 and 6. Yes. Let's also do B intersection C. What is that? Look at them carefully. You have 3 and 9, right? Now notice something. Notice that A intersection B is the same thing as B intersection A, right? Which is they're the same thing as 3 and 6, right? So what is that called? That is called the commutative law, right? That's called the commutative law. This is called commutative law. Commutative law, right? Or the law of commutation. You know, when two things commute, they can interchange, right? Okay. Now let's do more. Now suppose we'll find A intersection B, right? And then intersection C, like that. We'll put A intersection B in bracket. If we'll find out, what do we find? Basically, what that is saying is we already find A intersection B, which is we got 3 and 6, right? And then if you intersect that with C is over here, then that will be like that. You can do that again. This is the mathematics, man. You know, nothing is, you're not breaking any law. So, what do they have in common? They have 3 and what? Only 3. They have 3 in common, right? That's all. That's all they have in common. Now, let's do the other side too. Let's do A intersection, then in bracket, B intersection C. Right? Look at them carefully. What do we have? We'll have A, which is there, 1, 3, 6, right? B intersection C. What is that then? Intersection C. What is that? It's right here. We'll have it right here. Okay, it's 3 and then 9, right? So you do that. What do those two have in common? They have 3. They don't have anything else, so they only got 3. Notice that these two things are equal, right? So we'll say that A intersection B in bracket intersection C is the same thing as A intersection B and intersection C in bracket. You see, those are the same thing, right? Those gives you equal result. This is called associative law, right? Associative law. You can say the law of association. That's all that says, man. All right. We still continue with the same problem, right? I just want to write I wrote the problem down here. That way you can see what I'm doing. See right there, A, B, and C. The same problem, right? You can see that. So let's continue. Now, suppose we'll have this. Suppose we'll have. I want to do this first. Let's do B union C. Remember, by now you should know how to do union. The elements of those two sets, not anything common, but all the elements of those two sets, right? That's what union means. So let's do that. B and C. You have B here, you have C here. Combine the elements, you get 1, 3, no repetition, right? 6 and 9, right? That's it. Okay, because why I did that, there's something else. We're going to prove another law. Just keep watching. And then we want to do A intersection B union C. That's not how you write it, sorry. That's like that. You write it like that. Okay. We got B union C. And now we know what A is right here. So if you want, you can write it like this. A1, 6, all right, intersection 1, 3, 6, 9. If that helps you to visualize what you're doing. What do they have in common, those two sets? They have 1, they have 3, and they have 6. They don't have 9, all right? So that's what you said there. Now, let's find, we found that already. A intersection B, I think it's up here before. But we can find it again. It doesn't matter. I don't want to go back and forth. Let's find A intersection B. We can find it again. It's 3 and 6, right? Now, A intersection C. What is that? It's 1 and 3, right? Okay. Now, here's what we want to do. We want to find this thing, A intersection B union C. That's what we want to find. And we want to prove that it's equals to A intersection B, right? Union A intersection C. It's a long one, man, but I will explain it to you. Notice that this one is what? Is that one there, right? Which is 1, 3, 6, right? That's what we got here. And notice that this one here is what? Well, we need that one. We'll have to find that one. How do we find it? We already have a intersection B, we'll have A intersection C, we'll have. So basically, we're looking for, and that are equal. So this is equals to this here. Because this one is also 1, 3, 6. So they're both equal. So the law we prove there is called it's called the distribution law. But what happens is, the way they say it, they say it's distribution law, right? Distribution law. So in this case, intersection distributes, right? Intersection distributes, over union. Intersection distributes over union. Over union. Because you see, what is happening here? You have that, so this, right, gets sucked in there. And then you have A intersection B. And then you have union, also A intersection C. That's what you're looking at there. Okay, there is one more. We can find that. Here's how you find that. We do A union, then B and intersection C, right? That will give you, we got that because we got it before, 6 and 9, right? Okay. Yeah, we got it 1, 3. See, somewhere here. Well, that's what the answer, because what you're doing there, you taking A, right? What is B and B? B intersection C is somewhere here. Let me see. Yeah, we did find that area right there. B intersection C right here. So which is 3 and 9. So we then take that and intersect it with A, right? Which we can do. So, sorry, this problem is kind of long, man. If you do all that, you will get B intersection C as 3, 9, right? And then you get A union B, you get that as 1, 3, 6, 9, right? And then you get A union C, that's 1, 3, 6, 9, right? Okay, so once you get all that, then you're gonna see that A union B, right, in bracket intersection A union C. You're gonna see that is equals to 1, 3, 6, 9. That's that set there. Right. Once you get that, you notice that this is equal to that set. So in that case, you said that A union B intersection C is the same thing as A union B in bracket, then intersection in bracket A union C, right? It's a long one, man. But notice what is going on. Well, first of all, this law is called stale distribution law. Distribution law, right? It's distribution law, and this time, what is happening? The union is distributing over intersection, right there, right? To see that, notice this goes into that and get that, and then this goes into that again and get that, and then this intersection goes here. So look at it carefully. You will see what I'm saying. This has been a long one, man. So let's continue on the other side. All right, let's continue with the next topic, which is a complement. The complement of a set. The definition is right there. Let U be the universal set. The complement of a set A consists of the elements of the universal set which are not in A. It's written A with that like prime, or you can write it as A with C on top, the power. It's just A to power C, something like that. All right. So let's we need to do some examples. Complements have some property, but I'm not gonna worry about that. Let's do some examples. Right. The first example is this one here. Let the universal set be this set there 3, 7, 10, 17, 21, and let this set A be that set there. What is the complement of C? That's what we're trying to find out. The complement of C, right? What is the complement of what is the complement of A? Not C. What is the complement of A? Right? So what you do is you proceed. Just remember the definition. A complement, right? The complement of A is the elements that are in the universal set, but it's not in A, right? So look at that, the set carefully. You see 3 is there in the universal set, but it's not in A. And then you have 10, you have 21. No, actually 21 is there, sorry. 21 is in A. So that's right there. That's the complement of A right there, given that setup right there. Okay? So we'll move on to another example. You are given the universal set is a set that is X, such that X is a state in the west coast of the United States. And A consists of Washington, Oregon, and California. Those are the states in the western coast, right? What is complement of A? Again, if you know the definition of complement of A, the complement of A is an empty set because there's nothing in A that is not in the universal set, right? So that I chose this example carefully. That way it helps you understand the definition, right? So let's move on. Let's move on to something else. Now, our next topic is the difference of two sets, right? Now, suppose you have two sets. How do you determine their difference? Again, the definition is there. The difference of two sets A and B, right, is denoted A. It's like A minus B, right? It is the set of all the elements in A that are not in B, right? In other words, it's a set consisting of elements which belong to A but does not belong to B. That's how you explain that. Look at how it's, they use a set builder notation to define it. It's set such that X is in A but X is not in B. Very simple. Okay, so let's do example. This is example right there. A is that, B is that. What is A minus B? The difference of A and B. That is, according to the definition, is this. 6 and 7, yes. See, 6 is here, 7 is here, but they're not here. They're not there. So it's the set that consists of the elements in A that are not in B. Basically, 6 and 7 are in A, but they're not in B. So that's it right there. So let's do another example. You are given two sets there. What is the difference, right? The difference is this set right here, 12, 19. How do you know that? Because 12 and 19 are in set A, but 12 and 19 are not in set B. Okay? So let's do one more example. Look at that. A is that set there, and B is that set there. I made that up. I make all the problems up. Notice that A is all the states in the western coast of the United States, Washington, Oregon, and California are abbreviated. And then set B is all the states somewhere, including California, right? So P is Pennsylvania, T is Texas. So what is the difference? What are the things in A that are not in B? The answer is W and O, right? Because Oregon is here, Washington is here, Oregon is here, but they're not here, right? But see, California is there, and California is here, so you don't include California, all right? So let's go to another topic, man. All right, the next topic we'll have, which is the final topic for this video, is called the Cartesian product. That's the definition there. The Cartesian product of two sets, A and B, denoted A times B and read A cross B, is the set of all distinct ordered pairs whose first elements belong to A and whose second elements belong to B. You see? So here is how you represent it using the set builder notation. A times B is equals to ordered pair X and Y such that X belongs to A and Y belongs to B. You can also do B times A because they are set. You can switch it around. B times A is equals to the ordered pair X and Y such that X is in B, Y is in A. Okay, X is in B, Y is in A. Okay, so then note this carefully. A times B is not necessarily equals to B times A. So you have to be very careful when you're dealing with ordered pair. They may not be equal, they may look, they may come from the same set, but they may not be equal, they're not necessarily equal. So let's do some examples. Right, here is the first example. You see set A there, set B there, and then they want to find A times B, right? The Cartesian product of A and B. And then the Cartesian product of B and A. All right? You proceed like this. Now you're looking for a bunch of ordered pairs, right? And then they all constitute a set. That's all. So you can start like this, make a set symbol, and then start. The way you do this, you take two you multiply. I'm sorry, you take 2, you order, you put it together with A. You take 2 again, you put it together with O. And then you continue. You take 3, you put it together with W. You take 3, you put it together with O. That's all. So when you do that, you will have 2 and the W are in one ordered pair, right? Sorry about that. Okay, comma, because the ordered pairs are in a set. And then you go do this next one, 2 and O. That's not 0. That's actually this represent Washington, this represent Oregon. I chose that carefully. Okay, and then you go next one. Now you start with 3. Okay, 3 and Washington. And then 3 and Oregon. And then you close it off. That's it. That's it for that one. You're done with that one. Now let's do it the other way. We're just playing with the ordered pair. We're switching the order around, right? By doing B times A. So you do the same thing. You will get a W and 2. And then W and 3. Right? And then O and 2. And O and 3. Basically, that's it. That's what you're looking for there. Alright, let's do another example. See, just study it carefully. It's not difficult. You remember we did a lot of ordered pairs when we did the Cartesian coordinate system. So the idea comes from there too, Remember points. All the points in the Cartesian coordinate system represent an ordered pair. The first element is X element, the second element is Y element. That's the same idea here. The first element is the first set on the left. The second element comes from the second set on the right. That's all. Okay, let's do another example. I think I wrote it down already. Right there. You have 3 sets there, and they want you to find that they first want you to find A intersection B in bracket. There you multiply it by you do a Cartesian product with that and C, right? With that set and C. Okay. So first let's find the intersection A and B. We'll find that first, and that will give you this set here. Well, I'll write it out. 2, 3, right? Intersect 2, 3, 7. That's what you have up there, right? And then what do you get? Actually, I have to get rid of this one. Let me get rid of that. I'll come back to it. What do you get there? You get, you do what you normally do. Intersection means 2 sets. The common elements in 2 sets is intersection, right? What are the common elements in those 2 sets? You have 2, you have 3. That's it. Those are the common elements, right? Now you're gonna do the other part. You're gonna do right here. Look over here. You're gonna do A intersection B times. Now you're gonna do the Cartesian product times C. Basically, what you're doing is you're doing this here with this result here, and you multiply it. Now you can do this. This is legal. This is mathematics, okay? You can multiply with this set here, W and C. Okay, so that's the multiplication we're looking for. You go ahead and do what we did before. All right. When you do that, you get a set 2W ordered pair 2C 3W and 3C, like that. That's what you're gonna get. All right. Yeah, look at it carefully. That's what you're gonna get. All right. So please, I'm gonna stop here. Subscribe to my channel, like and share this video. Leave comments and questions under the video. If I have time, I will get to them. Okay. Thanks for coming. I'll see you next time.